Hi, welcome back. This is Professor Ridge, and today's lesson is on 6.4 matrix operations. Two matrices are equal. So here we're defining what it means to be equal. Two matrices are equal if and only if they have the same order. So if one's 2 by 3, the other one has to be 2 by 3. And corresponding entries are equal. So again, two matrices are equal if and only if they have the same order and corresponding entries are equal. So we can use this a couple different ways. Okay, so one way I can just ask a question like, are the following matrices equal, yes or no? So if A is 3, 2, 1, 4, negative 8, 3, and B is 3, 2, 4, negative 8, is A equal to B? And the answer is no, and because the order is not the same. A is a 3 by, order is not equal, or the same. Okay, A is a 2 by 3, A is a 2 by 3, and B is a 2 by 2. So they're not the same order, so they can't be equal. Alright, so first you check the order. If the order is equal, then you look at each entry and make sure the entries match also. Okay, so A, B, so if I had A is 4, 5, 2, negative 7, 3, 8, and B is 4, 5, 2, negative 7, 3, 8, you can see the answer is yes. They're both 3 by 2, and each entry, corresponding entry, are equal. Okay, so another way I could use this property is I can say, all right, these two matrices are equal, and then ask you to find x and y. Now for these to be equal, they both have to be the same dimension, and which they are, and then each corresponding entry has to be equal. So you can see the 3x has to equal the 12, the 2 has to equal the 2, which it does, the 4 has to equal the y minus 1, and the 7 equals 7. So basically I just have to solve this to find x, and solve the 4 equals and solve this for y to find the y. Okay? And again, the idea is I'm making a statement that these are equal, so the only way they can be equal if they're both the same dimension, they're both 2 by 2s, so that's fine, and each entry, corresponding entry, has to match. So 3x equals 12 would say, well, if 3x equals 12, then x must be 4. And if 4 equals y minus 1, then y must be 5. Okay, so that's another way I could use that property. Okay, so to add or subtract two matrices with the same order. Now that's key. They have to have the same order. This is key here. Now all you do is you just add or subtract the corresponding entries. And then note, if the order is not the same, if one's a 3 by 2 and the other one's 2 by 3, you can't do it. Okay, they have to have the same order. Alright, let's try a couple of these. Okay, so we got these two matrices. A is 3, 4, 5, negative 2, 1, negative 3, and B is 1, 5, negative 2, and 6, negative 3, 1. And they're both 2 by 3s. So we can add them because they have the same dimension. So what you're going to do is for A plus B, we're going to add the corresponding entries. 3 plus 1, 4 plus 5, 5 plus negative 2. And then for the second row, corresponding entries be negative 2 plus 6. 1 plus negative 3, and then negative 3 plus 1. So we get 4, 9, 3, and then the second row would be 4, negative 2, negative 2. Okay, so that's A plus B. Now if I wanted to subtract these, I'm just going to subtract the corresponding entries. So it'll be 3 minus 1, 4 minus 5, 5 minus a minus 2. Okay, that's row 1. Row 2 would be negative 2 minus 6, 1 minus a minus 3, minus 3 minus 1. So I would get 2, negative 1, 7, negative 8, 4, negative 4. Okay, so that's how you add and subtract two matrices. So again, the key has to be, they have to be the same dimension, and then you just match up the entries and add them or subtract them, whatever you're doing. Alright, so now scalar product is, or something, you'll hear me say scalar multiplication, same thing. Scalar product or scalar multiplication. The scalar product of a number k in a matrix A, denoted Ka, is the matrix obtained by multiplying each entry of A by the number k. The number k is called a scalar. So A is a scalar, and the scalar product, again, you get it, obtain it by multiplying every entry in A by whatever k is going to be. So I'm going to use the A and B that I did for the previous example, since I'm running out of room here. And so if I want you to find 5A, this is what's called scalar multiplication or a scalar product. And we're going to take every entry in A and multiply it by 5. So we're going to go 5 times 3, 5 times 4, 5 times 5, negative 2 times 5. Oh well, 5 times negative 2, I'm sorry. Doesn't matter. You still get the same result, right? So then 5 times 1 and 5 times negative 3. So that's going to give us 15, 20, 25, negative 10, 5, and negative 15. Okay? So if I did negative 3b, you're going to multiply every entry in b by negative 3. So it's negative 3 times 1, negative 3 times 5, negative 3 times negative 2, negative 3 times 6, negative 3 times negative 3, negative 3 times 1. And we get negative 3, negative 15, 6, negative 18, positive 9, and negative 3. Okay, so that's how you do the scalar multiplication or scalar product. Okay, so pretty straightforward. It pretty much behaves like distributive property. It's pretty analogous to distributing. So you take the 5 and multiply it with everything inside the brackets. Okay, for each entry. So 5 times each entry. Okay, some properties of matrix addition and scalar multiplications. I would say you probably don't have to memorize this, but just for me to show you, we kind of cover it in the book here. If you have matrix A, and it's typical that you name matrices by capital letters. I haven't mentioned that yet, but that's the way you do it. And then the entries inside the matrix A, you would use a little a and use subscripts for the row and the column that entry's in. Okay, so we're not going to really get that far into it right now. but you might see that. So it turns out that matrix addition is commutative. So whether you do A plus B or B plus A, you get the same answer. It's also associative. So just like with real numbers, for matrix addition, same, it's associative and commutative, meaning you can group it. I can do A plus B, get an answer, then add C. Or I can do B plus C, get an answer, and then do A plus the answer of B plus C. And either way, you're going to get the same result. Okay, and then for scalar multiplication, if you're going to multiply K times L, you can multiply those numbers first and then multiply it in with each entry, or you can do it L times each entry in A, and then multiply the K with that. So either way, you still get the same result. If you take a scalar times the sum of two matrices, you can do the scalar times each matrix, and then add the two together. Okay, so that's just like that. That's the distributive property. And the proofs of all these would be you just go back and basically you cite the properties in real numbers, because all the entries are real numbers. So if you add two real numbers, you can add, they have commutative, associative, so on. So they're pretty easy proofs, but we're not going to do that either. Okay, and the next one, if you had K plus L times A, that's the same thing as K times A plus L times A, another distributive property. So in this one, you're adding two scalars. Two scalars, again, are just regular numbers, and A is a matrix. So I can do, so if I had like 3 plus 5 in parentheses, I can get 8, and then I can do that to each entry, or I can do 5 times A and 3 times A, and then add those together, and I'm going to end up with the same result. Okay, so that's another distributive property. Okay, so there's we call this a zero matrix. So there exists a zero matrix, a matrix 0, such that any matrix A plus 0 equals 0 plus A, and again, this is not 0, the number 0, it's the zero matrix. So the zero matrix plus a matrix A equals just A. And so basically, so here, let me just tell you an example of a zero matrix. Might be something like 0, 0, 0, 0, okay, which is different than the number 0, because remember, this is a matrix. Okay, it could be whatever dimension, but all the entries would be 0. That's the zero matrix. Okay, and then also we have the additive inverse property, which says that there's a unique matrix, the opposite of A. So again, you're going to read this as the opposite of A. You might say negative A, but again, technically you should think of it as the opposite of A. So any matrix A plus the opposite of A, and again, that's a matrix A, is equal to the opposite of A plus A, which equals the zero matrix. So in the book, they have this as, bolded. So you know the difference between the zero matrix and the number 0. So that's the additive inverse. Alright, let's just use a couple. So those properties up there are just good to know. I'm not going to test you directly on them. Just tells you have some freedom again. So 3A, remember that's scalar multiplication, so 3 times A would be You can do 3 times each entry, so it's 3, 6, negative 12, 9. 2b, so you're going to do 2 times each entry in b, so that would be 8, negative 6, 2, 4. And then now to add these two matrices, you're going to add the corresponding entries. So we're going to get 11, 0, negative 10, 13. And then we're done. What's 0c? And that's equal to not 0, it's the 0 matrix, which is going to be, so 0 times any number is 0, but this is 0 times the matrix, and that's what I was talking about. I didn't even have that as a property listed above. Okay, but basically think of it as scalar multiplication. You're going to multiply each entry in C by 0, so you get 0, 0, 0, 0, which that's the 0 matrix. Okay, what's A minus B plus, how about 2C? So that's going to be A minus B, which is going to get me, A minus B is going to be 1 minus 4, 2 minus a minus 3, negative 4 minus 1, 3 minus 2, then 2c would be negative 4, 2, 10, negative 2. So I'm going to add these together. So 1 minus 4 is negative 3, plus negative 4 is negative 7. 2 minus a minus 3 is 5, plus the 2 is 7. Negative 4 minus 1 is negative 5, plus 10 is 5. And 3 minus 2 is 1, plus the negative 2 is negative 1. Alright? Okay, I'm not going to write the way the book refers to matrix multiplication. I'm going to explain it, and we'll see if we can get through this here. So this is a, if this is A, and B is, now notice, no, A, the order of A is 2 by 3. 2 rows, 3 columns. Now to multiply A with times B, I have to make sure that the row of A matches the the column of A has to match the rows of B. So this could be a 3 by whatever I want it to be. And I'm just going to make it small, 3 by 2. So for B, I need 3 rows, and 2 columns. So maybe I do 2, negative 5, 1, 3, 4, negative 2. Now this is going to be equal to a 2 by 2 matrix. Okay, so what you do is you got 2 by 3. You're going to multiply it with a 3 by 2. These have to match up and then kind of go away, and you're left with the 2 by 2. Okay, that's the first thing you analyze. So if note, if I did a 4 by 5 times a 3 by 2, see, they don't match. That has to equal that. So they don't, means you can't do it. Can't multiply. Okay, so the rows, the column of the first one has to match the row of the second one. Okay, now, the way you do this, okay, this can get real confusing, is I'm going to take the row of the first one and a column of the second one, and I'm going to match up the corresponding spots and multiply them. So I'm going to take, so A times B is going to be equal to, I'm going to take the row, the 1, 2, 4, and I'm going to take match the first one with the first one. It's hard to say that, huh? So it's 1 times the 2, the first one in the row of A times the first one in the column of B, plus, now I go to the second spot, 2 for the row times the negative 5 for the column, and then I go to the third spot, 4 from the row of A times 1 from the column of B. So that's this result, 1 times 2 plus 2 times negative 5 plus 4 times 1, that goes in the first row, first column spot of the product. And now I'm going to move to the first row, second column. So I'm going to take the first row, second column, and I'm going to match them up again. And we have the 1 times the 3 plus 2 times the 4 plus 4 times the negative 2. And that goes in the first row, second column spot. Okay, now I'm done with the first row. Now I do the second row. So I'm going to take the second row of column of matrix A, and I'm going to match it up with the first column of B. So I'm going to get negative 3 times 2 plus 1 times negative 5 plus 5 times 1. So that's the second row, first column. So I did the second row, first column. And this is the second column. Okay? So now I just got to do the second row, second column. So I take the second row of A and match it up with the second column of B. So negative 3 times 3, 1 times 4, plus 5 times negative 2. And I punch all that in my calculator. I don't have a calculator right now handy, so I'll just do it with my hand. 2 minus 10 plus 4, 3 plus 8 minus 8, negative 6 minus 5 plus 5, negative 9 plus 4 minus 10. So that's going to be negative 4, 3, negative 6, negative 15. So that's my answer of A times B. Alright, let's try another one. Find A times B. So first note, right, look at the dimensions, or order, right? So we got A is a 2 by 3. And we're going to multiply that with a 3 by 3. So again, the row of the first one, the column of the first one has to match the row of the second one. Those match, so they kind of disappear, and then we're going to get a 2 by 3 as our final result. So A times B will be a 2 by 3 matrix. Okay, so I'm going to take, so AB is going to be equal to, and again, I'm going to match the row, I'm going to do row 1, column 1, and put the result of that in row 1, column 1 spot. So it's going to be 2 times 3 plus 5 times 4 plus 4 times 6. That's row 1, column 1. Now I'm going to do row 1, column 2. So it's going to be 2 times 1 plus 5 times negative 2 plus 4 times 1. Now I'm going to do row 1, column 3 and put it in row 1, column 3 spot. So 2 times negative 2, 5 times negative 1 plus 4 times 2. Okay, now I'm going to do row 2. Row 2, column 1. So I'm going to do 1 times the 3 plus negative 4 times the 4 plus 3 times 6. Then I'm going to go row 1, column 2. So row 1, column 2. 1 times 1, negative 4 times negative 2, 3 times 1. Okay, so that's row 2, column 2. Now I got to do row 2, column 3. See, and I just go order. You can go in any order you want. Just remember, if you want the number that goes in row 1, column 2, you got to take row 1 times column 2, match them up, multiply them, and add the result of each corresponding entry. Okay, so now I'm in row 2, column 3 is the only one I have to do. So that's 1 times negative 2 plus negative 4 times negative 1 plus 3 times 2. Now just punch in each one of these entries into your calculator and write down the result. Again, I don't have a calculator handy, so I'll just do it. 6 plus 20 plus 24, 3 minus 16 plus 18, 2 minus 10 plus 4, 1 plus 8 plus 3, negative 4 minus 5 plus 8, negative 2 plus 4 plus 6. So that's going to get me, see, 50, negative 4, negative 1, 5, 12, and 8. Okay, so that's matrix multiplication. Alright, and one more thing. I'm going to squeeze it in this page. Note, AB does not equal BA. Okay, so matrix multiplication is not commutative. Okay, you can represent a system of equations using what we call a matrix equation. So the idea is if we had, say, let's do something easy, 2x plus 3y equals 7, and 4x minus 5y equals 2. What you do, instead of using augmented matrices, you're going to do the coefficient matrix. So we're going to do a coefficient matrix times the variable matrix, and that's going to be equal a constant matrix. So coefficient matrix times the variable matrix and that's going to equal constant matrix. And the way you do it is you're going to write, so A is going to be the coefficients. So you're going to put the x's in the first column, 2 and 4. Y is in the second column. The variables, we're using x and y. And C, the constants, will be just the 7, 2. Okay, so the way you'd write this matrix is equation is you're going to write 2, 3, 4, negative 5 times the variables x, y equals the constant 7, 2. And it's simple as that. And if you did the matrix multiplication, you take the 2, 3, row 1 times the variables x3, and you would get, so note, if you multiply these two things, you're going to get 2 times x plus 3 times y. So this is a 2 by 2 times a 2 by 2 times a 2 by 1. That's going to get me a 2 by 1. See? So it jives that way. So I take the first row, first column, get 2x plus 3y. Take the second row, first column, 4x minus 5y. And then from what we learned at the very beginning of this is these two matrices are equal only if the entries are equal. So then 2x plus 3y equals 7, 4x minus 5y equals 2. And you get the system of equation. Okay? So you can take a system of equations and write an equivalent matrix equation that represents the exact same system of equations. So let's try that. Alright, so let's try one more example. We have this system of equations. 3x minus 2y plus 4z equals 8. X plus 3y plus 7z equals 15. And then the last equation, 5x plus 2y minus z equals 12. So again, the way we're going to do this is we're going to write the coefficient matrix. So you can either work, I like to just work in columns when I do this. So the x's are 3, 1, 5. The y's are negative 2, 3, 2. Z's are 4, 7, negative 1. So that's the coefficient matrix. The variable matrix will be 4, the variables are x, that's an x, believe it or not, y and z, and then the constants are 8, 15, 12. And that's the matrix equation that represents the system of equations. Okay, so that concludes the lesson for 6.4. Go to My Math Lab, complete your exercise there, and I'll see you next time.